Hello, good morning, everyone. Let's go ahead and get started. My name is John Bandela. I work on the hotels search backend team at Google, and I'll be talking about polymorphism not equals virtual, flexible runtime polymorphism without inheritance. So the question, what is polymorphism? Many forms. That's the answer. All right? You'd be technically correct if you said that, but it's not a very helpful definition. So let's see if we can get a more helpful definition. Providing a single interface to entities of different types. Right? And it's important to understand that polymorphism actually predated object-oriented programming. Consider this expression. A plus B. It does different things even though it looks the same if A and B are integers, if they're reals, if they're complex numbers, if they're vectors, or if they're matrices. But we're using the same notation for each of these situations. So we're going to talk about two main types of polymorphism during this time. We're going to talk about static polymorphism, and we're going to talk about dynamic polymorphism. So static polymorphism. Its main exemplar that we're going to focus on is overloading. And for dynamic polymorphism, we're going to talk about virtual functions. Now you may say, hey, we're in C++ 17, what about variant? Well, variant, the types of a variant that it can operate on are a closed set. The operations a variant can do are open. For the purposes of this talk, we're going to focus on polymorphism that has the types as an open set and the operations as a closed set. So it's kind of the inverse of variant. So let's give an example. And this example will be with us throughout our talk, and we will implement this in different ways. Let's say we have a shape, and we can draw the shape. We can get bounding box. We can translate it, and we can rotate it. All right, so let's look at overloading. So overloading, we determine at compile time which function to call based on parameters. There are many, many rules. Any show of hand, how many of you feel that you completely understand C++ overloading? All right, yeah. I don't know, but in general, it just works. And the nice thing about it is there is no runtime overhead. All right. So let's consider this. We have a class circle, right? And we've got 4 member functions. Draw, get bounding box that returns a box, translate, and rotate. By the way, the reason for the last example is every CppCon speaker is encouraged to try to use the words rotate in one of their talks. All right. And what about the box, right, that we returned? So basically something simple. We have methods or member functions to get and set the upper left and lower right. And finally, we have a member function that takes another box and determines if it overlaps. All right. So let's do an example. So let's write a function called SmartDraw. And SmartDraw is going to take a shape and a box representing the viewport, right? And it's going to get the bounding box. And if the viewport overlaps the bounding box, it will draw it. If there's no overlap, there's no sense wasting our time trying to draw something that no one will ever see, right? This is if a tree falls in the woods and nobody hears it, did it fall? Or did it make a sound? All right. So let's also type this thing called spin, right? So we take a templatized parameter, shape, S, and we call translate, and we call rotate on it. And we're going to be using these two functions throughout the rest of this talk. So how do we use this? We create circle somehow, we spin it, and then we draw it. What about box? Right? So drawing circle C and smart draw, that works. But doing box B and smart draw, that doesn't work. Now in our minds, like box is also a shape, right? Like why can't we easily draw it? Right? That doesn't work. What should we do? Well, if you studied object-oriented design patterns, you would say, oh, let's write a facade. Let's not do that. All right. Instead, let's use overloaded customization points. Right? So we have smart draw, and right now, we're calling member functions. s.getBoundingBox, s.draw. And let's change these to instead call free functions. GetBoundingBox s, draw s. And the nice thing is we can provide a default implementation, right? So for everything, we call s.draw. But the nice part is we can now provide a box implementation without modifying box, right? We have enough information that box has that we can figure out how to draw it. All right, so this is our smart draw, right? So we call getBoundingBox, draw. And spin, we do the same thing. We've turned our member functions into free functions. Right, so how do I use this? I can create a circle, spin it, and smart draw it. I can create a box. I can spin the box, and I can draw it. And it works. The other nice thing about overloading is I have value semantics. I can create one circle. I can create another circle that's a copy of it. And if I spin the first circle and draw them both, they'll both be in different places because the second circle was independent of the first circle. We had value semantics. And value semantics are nice to reason about correctness and to reason about concurrency and thread safety. What about low coupling? Consider smart draw. Look at the implementation of smart draw, the getBoundingBox and the draw. What operations does this depend on? Right? getBoundingBox and draw. We're depending only on the operations that we're actually using. We're not depending on all the other operations that the type provides. We're just depending on our own. All right? The next thing that it does nice is what I call PPP. Anybody know what PPP stands for? Purchasing power parity? No. So it actually stands for Parents Polymorphic Principles. All right? And they are the requirements of a polymorphic type, by definition, comes from its use. And there are no polymorphic types, only a polymorphic use of similar types. And both of these quotes are from Inheritance is the Base Class of Evil by Sean Parent. So if you're watching on YouTube, if you haven't seen that video, search for it and watch it. It will open your mind to a new way of thinking about stuff. All right, so what are we doing here? So according to this, we're using getBoundingBox s and drawX. We're not requiring them to be a different type. We're not requiring them to be inherited. We're just using types polymorphically. The types don't have to buy into it. All right, we passed that. So, in review, what has static polymorphism ever done for us? It's given us low boilerplate. It's easy to adapt an existing class. We just had to provide some overloads. We have value semantics. We have low coupling. We just depend on the operations that we actually use. We follow the polymorphic principles, like the use of polymorphism is defined by its use, not by the type's definition. And we have good performance. It's static dispatch. It happens at compile time, figures out. Obviously performance, right? I mean, it's static, it goes without saying. All right. Can we stop now? Are we done? Well, no, we're missing something. We have some problems with overloading. Two main issues. First, we require everything to be a template and thus live in a header, right? Our smart draw takes shape as a template parameter. So it needs to live inside a header file. We can't just put it in a source file. If we do this everywhere, we're going to really stress test modules pretty well. All right? The other issue is we can't store it in runtime containers, right? Vector, it'd be nice to have a vector of shapes. And we push back a circle, and we push back a box, and we can do stuff with it. But we can't express it in a type. All right, so let's go to the other side. Let's look at virtual. What can it do for us? So we can have an interface, right? Struct shape and draw, and these are pure virtual functions. Get bounding box, translate, rotate. What have we forgotten? Don't forget the virtual destructor, right? It's something to remember, right? It can, you know, if you're not paying attention, it'll trip you up and you'll get weird errors. All right, so how do we define circle? So inherit from shape, do a bunch of overrides, draw, get bounded box, translate, and rotate. Let's look at smart draw. So we take in a shape, we take a certain shape by reference parameter, and we call get bounding box, and we call draw on it. What's the nice thing about this implementation versus the last one? We are no longer a template. I can take this, I can put this in a source file, I can compile it once, I can link it once, the compiler can deal with it once, I can put it in a library, I can do all sorts of nice stuff with it to optimize it, to optimize my time and the compiler's time. But look at this. All we use are get bounding box and draw. But we're requiring a full shape to come in. Shape has much more than that. So when we're testing it or we want to use it, like there's no reason that we need to rely on all the other things, but we are. So we've increased our coupling with this as opposed to the overload. So what should we do? Well, let's go back and let's split up shape. So let's take these two, draw and get bounding box, and pull them out into their own interface, draw interface. And let's get the other stuff, other remaining things, translate and rotate, and pull them out into their own interface, transforming interface. And then we inherit shape from both of these. So now, we take a drawing interface, and our get bounding box and our draw, we're just requiring what we use. We're not requiring excess stuff. And the same thing with spin. Transforming interface, translate, and rotate. So how do we use this? We can create a vector, unique pointer of shapes. We can do stuff with make unique and put them in there. And then we can range for through the shapes, call spin on them, call smart draw on them. Great. We're now able to store in standard containers, right? Like our two missing things that we couldn't do was move our functions out of headers and to be able to store the polymorphic values inside a vector. Did we do it? Yes. We're able to be used in non-template functions and able to be stored in runtime containers. But what did it cost us? Right? So what are our costs? Before we had low boilerplate. Now we need an inheritance hierarchy. Before, we could take an existing class, not really modify it, just add an overload, and use it. Now all our classes had to inherit from a base. So now we had to consult the gang of four, or whatever design patterns, and write facades for all sorts of stuff. Before we had value semantics. Now we have pointer semantics. So now we need to worry about, hey, is this a raw pointer? Is this a unique pointer? Is this a shared pointer? Who else has a reference to this? Like, what are they going to do with it? We kind of have low coupling, but that's because we were either very careful or very lucky in how we split up our member functions, right? If we had split them a slightly different way, like we did originally, which made sense, we would have been coupled. We would have had extra dependencies. And like I said, the parents' polymorphic principles, our types are no longer, we're not using polymorphism just as a set of related types. Our types have to buy in, our types had to declare they're polymorphic. And performance, well, I mean, there's an inherent overhead in runtime dispatch, and given the increased flexibility, I mean, that's probably worthwhile. So what would we like? What's our wish list? So we'd like low boilerplate. We'd like easy adaptation of existing classes. We'd like value semantics. Low coupling. The polymorphic principle, like where the types don't have to declare themselves to be polymorphic. We just use them in a polymorphic manner. And performance, we'd like, we're going to have runtime dispatch, but we'd rather it be okay, acceptable. We'd like to be able to be used in non-template functions, so we can have separate compilation. And we'd like to be able to store them in runtime containers. And for the purpose of this talk, we're going to place a couple of constraints on ourselves. So whenever you see a C++ problem, a first thing that sometimes comes to mind is, let's use macros. But the problem is, now you have two problems, right? So no macros. And the other thing is, let's just use standard C++ 17. Just see how far we can get. Well, it turns out there's already a solution, and it's been there since C++ 11, and it's in the standard library, right? Let's do a history lesson. Anybody here read the Gang of Four design patterns book? Okay. Anybody here read Andre's Modern C++ Design? Okay, really good. Awesome. So in 1998, the standard came out, and we had this weird thing called a command pattern, right? So we had this command interface that had one function, execute. I think execute was so much that, I think somebody wrote an essay called Living in the Land of the Executioners. And we had this command interface, and you'd derive from it, and you'd create a concrete command interface. And then you'd create a vector. So back then, we didn't have any standard pointers that would actually go into a vector, so people did raw pointers. And they'd add stuff to commands via new, and then I could iterate through them and call execute on commands. 2011, we don't do command anymore, right? We do std function void, right? And we do range 4 now, and we just call command, right? So all our whole infrastructure with all the pointer semantics and everybody deriving from this and everybody writing adapters for this just went away. So std function, it does a lot of what we need. We have low boilerplate. We have easy adaptation of an existing class, right? We can take a functor, we can take a lambda, we can take a regular function, and we can put in an std function. It just works. It has value semantics, like we can make copies of them. We have low coupling, right? We can just take in whatever, it just depends. Do you have a function call operator? Can I make a function call with this signature? And we adhere to the polymorphic principle, right? Like a lambda doesn't say, oh, I'm a polymorphic lambda, or I'm trying to be a polymorphic lambda, or you can write a functor and you're not how to inherit from anything. Or you can take a regular function, and they all just work together. We're defining our polymorphism not by how the type is defined, but how we're using them. And we have decent performance, I mean, give or take. I mean, there's an inherent overhead in runtime dispatch. And like we said, we're able to be used in template functions and able to be stored in runtime containers. So std function. So what is this that I'm highlighting? So this is called a function type. This has the information on the parameters and the return type of the function. We can examine the parameters and the return type using partial template specialization, right? And the other thing is function ref. So it turns out a lot of times when we're passing stuff to functions, we actually don't need an owning type. We can just pass a reference type instead of an owning type. I don't believe it's standard. There ongoing work on standardization, but there's a bunch of open source implementations you can find. So we got function and we got function ref. Are we done? The problem is we only support a single operation, the function call operator, right? Like we want to have interfaces that have more than one function, right? We want to have arbitrary number of functions. We want to be able to do different stuff and call different stuff. So then we come to the issue, how do we name the operations? We can use a function name, void rotate, right? And we're all familiar with it. We do everything. What's the problem with using function names? Well, it turns out C++ 17, unless you use macros, can't metaprogram names. If I tell you, oh, here's rotate, what can you do with it? Not a whole lot unless you're using macros. However, if we name the operation with a type, right? So rotate is no longer a function. We make it a struct. And then our rotate signature, we encode the operation inside the signature, right? So now we've turned from a function name, naming an operation, into a type. Now, if one thing C++ 17 is really good at, it can metaprogram like a boss with types. All right, fanfare. So now we're introduced who's going to be the star of the show from this time forward, polymorphic. And you can find it here. It's a single header file. All right, first of all, 3 important things to say about polymorphic. This is not an officially supported Google product. This is not an officially supported Google product. This is not an officially supported Google product. All right, are we clear on that? So don't go to Chandler if you have problems with polymorphic. You can always email me. All right, so polymorphic combines aspects of virtual and overloading. So we're able to specify an interface like virtual, and we're able to use overloading to connect a type to an operation, and we call our extension point polyextend. All right, so let's see how we specify an interface. So with virtual, this is what we're doing. Look at transforming interface. Translate, $x, $y, rotate, and spin, use the transforming interface. How do we do it in polymorphic? We take struct translate, struct rotate, and we take polymorphic ref, void translate double, void translate degrees. Now what's interesting is you can actually, when you're declaring a function type or using a function type, you can actually name the parameters in there. The compiler doesn't do anything, but they're often useful just for documentation purposes. So basically what we've done, we've taken these function names, made them types, and then moved them inside the function type. So that's the first part, specifying an interface. Now, let's use overloading to connect an interface to an operation. So in overloading, what did we do? We had 2 functions, translate, right? 2 overloads of translate. First one did it for everything. Translate, and we just called s.translate. And then we had a specific overload for box, so box B. How do we do this in polymorphic? So instead of having every function overload be a different name, we name them all the same, polyextend, and we put in translate. So we've moved from naming by function names to naming and dispatching by types. So let's look at how we do spin. So virtual, we took in the transforming interface, S, and we called s.translate, s.rotate. For polymorphic, we're going to do this. Spin, we take the polymorphic ref, and instead of calling translate rotate, we call a member template function called call, very creative naming there, call and pass in translate and rotate. So now for our dispatch, we're dispatching not on the function name, but on the type. All right. So how do we use spin? We have class box, and we have class circle. And you will notice this is the exact same definitions we use with overload examples, right? So we can use box, and we can use circle, and when we define them, we don't have to be concerned about, are we going to make this a polymorphic type? We just define the operations that we want. So we can create circle C, box B, we can spin C, and spin B. Right? There are no polymorphic types, only a polymorphic use of similar types. What about const? Right? SmartDraw takes a constant shape, or it did. So virtual, right? We have the drawing interface. We make our draw and our get bounding box constant member functions. And we take a constant ref to a drawing interface. What do we do with polymorphic? Well, it turns out that you can actually add a const qualifier to a function type. And they have a wonderful name. They're called abominable function types. And they're not really useful for anything else except doing tricks like this, I guess. So anyway, we can call it const, and we can say bounding box equals call get bounding box, and s.call draw. And basically we're const correct now. Like we can encapsulate and encode const. All right. Now, how many of you have the west const? How many of you are west const here? How many of you are east const? Okay. Very good. So one of the big issues with west const versus east const is, how do you know the type, like what type is actually const? Like, right, a const pointer, like a pointer to a const, is different than a const pointer, right? So do we need another type to encode a constant ref? Well, it turns out we don't, because of this. As long as all the function types in a polymorphic ref are const, there's no way we can change that. So we can bind to a const type. We can bind to a const value, and we can store that as a constant void star inside. So we can basically say, can I ever change you through this ref? And by looking at the list of the signatures, we can know that you can't and automatically make it const. All right, so using SmartDraw, right? So I can do circle, and I can use asConst to pass a constant reference to SmartDraw. All right, so now I've covered my reference. Sometimes we need ownership. So let's do a polymorphic object. And that's akin to std function, right? So instead of ref, I just put object. And then I can put the draw, get bounding box, translate, and rotate. And the nice thing is, I have value semantics with that. Shape S1, create it with a circle, S2 equals S1, spin S1, and S1 and S2 are different. I didn't affect S2 when I modified S1. So I have value semantics. It's good for me. It helps me reason about logic, about isolation, and about concurrency. All right, what's the other nice thing I can do? I can store this in a collection. I can create a vector of shapes. I can push back a circle, push back a box, and then call smart draw for auto. I've got low coupling here. So with virtual, we had to carefully group our member functions to avoid coupling. Right? Like we had to go back and split our shape into a drawing interface and into a transforming interface. With polymorphic, it doesn't matter how we group functions. We don't have to worry about that. So how do we do conversions? So for example, smart draw takes a polymorphic ref, right? And the ref has draw and box get bounding box. In shape, well, I put draw and bounding box at the top. So this is kind of analogous to upcasting with inherited types, right? Well, this also works. I can move draw all the way down. And no matter how I arrange the order of these operations, as long as my ref can be satisfied with those operations, it'll convert any type that satisfies it. So now I don't have to think a priori about, oh, how am I going to structure this to minimize my dependencies, to minimize coupling. All I do is just, hey, I have this bag of operations I'm going to support, and whenever I use them, I have these operations that I require, and if I can get those operations out of the bag, I'm good. So how much does it cost in terms of our benchmarks? Well, before looking at benchmarks, there's lies, damn lies, and micro benchmarks. So this was just done on a Windows laptop. We fill a vector with different types of polymorphic objects, and then how long it takes to iterate and call a method on each item. So basically, yeah, using a non-virtual type really makes a big difference. Everything else is clustered around 500. You know, maybe a little bit bigger, a little bit slower, but in general, like, they're much, much worse than non-virtual, and they're all pretty close to each other. And what about our size? So size of ref is typically 3 times the size of a void star. And the size of an object is typically 4 times the size of a void star. All right, so final assessment. We have low boilerplate. We have easy adaptation of existing classes. We have value semantics. We have low coupling. We adhere to the polymorphic principle that a polymorphism is determined by the use of a type, not the definition of a type. Our performance, you know, it's in line with all the other indirect function call type stuff. We're able to be used in non-template functions. And we're able to be stored in runtime containers. So, show me the code, right? You can go there. And we can do all this, right? Like, we have all these capabilities, right? Like, we're actually more capable than we have with virtuals because, you know, we can arrange our methods however we want. We can do all these nice conversions. It's about 247 lines, including comments and white space. So how do we do this? So the heart of it is we generate our own vtable. So we use an array of function pointers. Each position of the array corresponds to a function type that is passed in. And for each type and each sequence of operation, there's a unique array. And each entry in the vtable contains a trampoline function to jump to the appropriate overload. So how's our trampoline function? So we take a type name T and a signature. And then we use partial template specialization to pull out the parts of the signature, right? So we've broken down the signature into a return, the method, and the rest of the parameters. And then we have this function jump that takes a void start T and the parameters, and it does a return type, and the same return type. And here, we just call polyextend with the method, and we call polyextend with the method. So now we're basically bouncing from the world of vtables to the world of overloads. And the other thing is because we we provide the t for this trampoline function. So even though we take in a void star t, we know we're safe, and we can safely static cast it to a static cast and dereference it, so we get a reference of type t, a tref. And then we pass that on to the polyextend overload. So how do we build a vtable from trampoline functions? Like I said, this is the nice thing with Variadics. We can write some really cool, nice, short, elegant code right there. 2 lines. So we take the trampoline function and passing in the signature and get the address of the jump function that we had, the static function. And we had to pick a type for it. And we pick an arbitrary function pointer type called vtable function, and we need to reinterpret cast the vtable from it. And the rule in C and C++ is you can cast pointer types between each other as long as you always convert them back to the correct type before you call them. So the next part will be, how do we do that safely? So call the vtable. All right, so let's have this vtable caller that takes a size I and a signature. And what we're going to do is we're going to overload the function call operator, and we're going to take the method and the parameters. So that way we can do correct overloading. Right? And what we do is we've broken our signature down into the return method and parameters, and we can use that to cast to the correct pointer type. So I'm using a little alias called pointer that's basically template type name t using pointer equals t star. And pointer actually makes working with stuff like function signature types to be much easier, at least for me, just less little bit of overhead. So anyway, so we've converted it back to the correct type. And if you remember from our view of the trampoline jump function, this is the exact correct function type, function pointer type of the jump function. And we take the size, so when we call it, we also get passed in an index, size t. And we use that to find where in the vtable is the appropriate pointer to function. And the next part, this is the part that allows us to actually have the functions and the function types to be able to be declared in any order and pick any subset. We actually don't directly index into the vtable. We first index into the permutation array, get that index, then use that to index into the vtable, right? So permutations, right? So we had the draw here, right? That was at the top. That's at the top of the list, position 0. But the provider of the vtable, right? They have draw at position 2, the third position, 0, 1, 2. So how do we go from, how do we translate this? So we have the permutation vector, which stores 2 and 0. So actually when I want to call draw, I actually need to call entry index 2 on the vtable. So then the other thing we do is we have a ref impl. And we can use one implementation that's parameterized to cover both the const, non-constant ref and the const and non-const object. And we have a holder type, a sequence, and a series of signatures. And the sequence is just std index sequence I. And what do we have in there? We have a pointer to the vtable. We have the permutations. And we have a holder. And a holder is an abstraction that basically allows us just to be like a void star pointer when it's a reference, or else it can actually be a copyable type when we actually have ownership. And what we do is, remember we had the vtable caller, and we overloaded the function call operator? Well, we can basically, the idiomatic overload in C++17, we're inherit from it using a function call operator. We can create an overload set of all the vtable callers, along with their signatures, and create a const expr static object called call vtable. And then we implement our call template method. So we are explicitly passed in the method, and we have call that takes in the parameters. And we just pass them on to call vtable, passing in an empty object of the method, our void star pointer, our permutations, and vtable pointer, and forwarding all the parameters. And then because we're overloaded there, we will match the best overload match for call vtable and call the correct entry in the vtable with that. If we can't, we'll get a compile time error. And then all that's left is to alias. So ref, we use pointer holder, and to pointer holder, we pass in one of two things. So if we have an std conjunction v, which means and, everything has a constant signature, we pass in constant void as the parameter for the pointer holder. So we end up with a constant void star. Otherwise, we pass in void, and we end up with void star. How about for the object? Here we do something interesting. So conditional T again, we check if it's constant signatures, and if they're all constant signatures, we can actually use a shared pointer to a constant. So a shared pointer to a constant actually has value semantics. So we can have large objects in there, and we can make copies of them, but as long as we can't modify them, as long as they're constant mutable, we can all reuse the same memory for all our copies. However, if we have anything that can modify it, we use value holder. And value holder is basically a type erase void star that can copy itself and return a void pointer. So polymorphic. Low boilerplate, easy adaptation of existing classes, value semantics, low coupling. We follow the polymorphic principles. Like, we don't care how we define the type, we care how we use the types. Performance is on par with all the other indirect function calls. And it's able to be used in non-templated code. And if you want to dig deeper, here's some references. There's the talk by Sean Parent. And in terms of like v-pointers, v-tables, and different storage thing, Louis Dion did like a really nice deep dive back in CppCon 2017. And the link to the library is there. Thank you very much, and I'll be open for questions.
Hi there.
Hello.
Good presentation, and thought it was really a cool use of technology. Have you considered, and I'm going to say the macro word to prepare yourself, using macro to make some of the syntax a little nicer, let's say, because obviously it doesn't feel very natural.
Yeah. So the question is, can we use macros to make it make the syntax nicer? I think, like, first of all, like, whenever we use macros, I think we create more problems with each other, with our long-term maintenance and our use. And the other thing is that right now, we seem to be in an era of introspection and generative programming for C++. And I believe this kind of provides like a nice, non-trivial, but not like research project-y example of something that people grasp. Like, hey, we can do this in 247 lines of code with these compromises in syntax. Like, so if you're coming up with like a new introspection or a new meta programming or meta generation, is like, here, this is a simple one that, hey, you're kind of like a hello world, and let's compare across the various implementations and things. So personally, I've been working on something called P1521, and that is using types as function names. So instead of naming functions by names, we name them by types. And it can actually get us out of a lot of quandaries that we currently experience in C++. It'll allow us to do universal function call syntax. It can allow us to do extension methods. allow us to do extension points and customization points without running into the problems that we have with ADL, blowing up everything. We can easily do overload sets. We can write forwarding proxies that will take a call on a member function and forward it on to some contained object. We can add monadic binding to pre-existing monad types without modifying them. And we can even write a monadic type that will automatically map bind based on what's being called. And just as my thing, so with that one, the translate, right, you have polyextend translate. This would turn into this, translate dot, which represents a type, dot paren. And our call, we get rid of the, how many people find angle brackets ugly? So yeah, I guess a lot of people do. Like they actually look like diamonds if you put them together. I guess you could rate C++ code like a diamond rating. But anyway, we can get rid of the, the angle brackets in the call just by doing something like this. S.translate, S.rotate, like passing in types. And like I said, that's my thing. But like there'll be others. And like I said, this is something you can do in like roughly 250 lines of code. You can present it in an hour. And so this can be kind of like, like a fizz buzz of, metaprogramming or other stuff that, that people can relate to. All right, next question. Sorry.
Hi. So I was wondering if we're working with C++20, this sort of the ref kind of mirrors concepts. I wonder if there's a way to, like, given a concept, generate the signature set or something.
Yeah, exactly. Like this is like kind of like, I think other languages have this thing of like they have the equivalent of concepts. Like I think Rust has like, I believe it's
Traits.
Traits, right. And then you can have like a runtime traits class and a static traits class. Right now with concepts, we just have the static. This would be really, really useful, but no obvious way to do this has come to my mind. But I think that'd be interesting. We could have like a similar thing that we could, like go directly from concept as a static thing to concept as like a dynamic dispatch thing. That'd be really cool.
Thank you.
Yeah, so you mentioned Louis Dion's talk on runtime polymorphism. Have you compared it to his implementation of this, like Dino?
So the big difference is he's using the C++ 17 extension of where you can pass in like strings as the to template parameters. I'm using types. This is more about kind of give the same interface as overloading, so a little bit more emphasis on jumping, but they can basically, you can do one with the other or go back and forth. They're very, conceptually they're pretty similar.
And one more question. So you had some benchmarks, but have you checked how well compilers can inline the calls when you're not actually using polymorphism, you're just using the types?
Well, if you're just using the types, you can just use the types directly. Right, because we're not doing any inheritance or anything.
As in, can the compiler determine that it can be inline when you're still using type erasure?
I haven't delved into that. My guess is probably virtual would have an advantage on that because the compiler already knows about stuff as opposed to this where it's just an array of function pointers.
Thanks.
Right, thank you very much.